So zircon, it's it really is a wondrous mineral. Most of you may be aware that zircon's used largely in dating, uranium-lead dating of rocks, to try and get a sense on how old they are. But not only that, we can also look at its isotopic character, and we'll talk about that today, specifically with oxygen isotopes and hafnium isotopes. Now, a lot of work and a lot of people have gone into this, and this is only a few of the collaborators in this space. But there's only so much room you can put up on a slide. So without further ado, I'll jump in now, and what I'll do is I'll try and make something relatively complex, simple enough to understand, and what are the impacts, why do you care, is essentially what I want to try and communicate. And if I don't achieve that, pull me up on it later. So you've seen the Stavely area largely in previous talks today, and I'll preface this by saying we're going to go from this whole area, zooming in through the magnetics into essentially the Stavely belt area, and it's really, really small. So we're only looking at a postage-sized stamp in this study, what I'm presenting here today. But if you wish to look for more regional geochronology and isotopic data, there are records that are attached to the end of this presentation. I'm not sure if they'll be provided to you digitally, but if you want it, it's on GA website and through the GSV. So where are we? We're essentially looking at the Stavely belt here. We have the Buckaran diorite and the Bushy Creek granodiorite. This is the GSV GA preferred model. The small area that we're looking at is really constrained to about 10 million years or so. So rather than looking at everything through here, we're just going to focus on 10 to 15 million years. There it is, 10 to 15 million years, around the sort of Delamerian time, and largely focusing upon the models that sort of reflect the Japanese-style arc system. Oh, there it is in a little bit more detail. So the rocks in question that we're going to be discussing today, we have the rocks from the Mount Stavely Volcanic Complex, and they include the Narrapummelup Road dacite member and the Tilmway Tuff. A number of the mineralised porphyries from core up at Thursday's Gossan deposit. The Buckaran diorite in the north. Now, what's important with this, I'll just draw your attention to it because it has implications later. We have two samples from the Buckaran, one in the sort of, the main central part of the northern body in the magnetic image, but there's also one on the very edge. We'll come back to that later. And the Bushy Creek, the Bushy Creek granodiorite is another sample we look at. We do have some geochronology on the Glen Thompson sandstone. That's in the reports, but I'm not going to talk about that today. But I will just mention now, it is isotopically highly evolved, and I'll explain what that means and what implications that has for the other samples. So you've seen the stratigraphic column in previous talks. We have the Glen Thompson sandstone correlated with the Cambrian 2 group, the Mount Stavely Volcanic Complex intruding that, Nargoon group above, and then the porphyries coming through and intruding the Mount Stavely Volcanic Complex, some older intrusions that we've intersected in core. I'll only briefly touch on those today because we didn't do any isotopic studies on those beyond uranium-lead, and the Bushy Creek and Buckaran. The yellow stars are the samples that we've analysed in the subsequent reports that we have provided. So here's an updated version of the time-space plot that you saw in Dave Taylor's talk. So prior to our project work in the Stavely area, there was a lot of disparate ages that sort of had a very large spread of almost 20, 30, 40 million years. And there's a lot of different techniques. So in the black here you have uranium-lead zircon dating. In the oranges and the blues you have mica, potassium argon and argon-argon dating. Tells you something different. and in the green we have some titanite uranium-lead dating. So all these different methods, minerals have different methods for dating and different standards incorporated into them. There's different levels of uncertainty, and really it makes it difficult to compare these ages. So one goal that we had was to take a lot of the rocks that already existed, sample them, and conduct geochronology using the single method, uranium-lead shrimp method at Geoscience Australia, collaborated with the GSV, using the single standard, and now we've really been able to sort of constrain some of the event ages within the Stavely Arc and surrounding granites to about 10 million years. We have some older intrusions around about the 510, 511 million years. Now there needs to be a little bit more work done on this. If there's any academic people in the audience, go for it, because I don't know if GA will look at these. We have the Mount Stavely Volcanic Complex here, a relatively broad spread if you consider this sample here, but we'll tend to look at these ones in here. We have the mineralised porphyries. Of note, I will just draw your attention again to those molly ages that were done by our collaborator Mark Norman. And this is that particular sample that Dave Taylor mentioned, which had the naughty sampling protocols attached to it. As you can see, the molly age is older than the age it's supposed to be hosted in. Bushy Creek and the Bushy Creek Igneous Complex here. What we've also gone and done, we've done CA-ID TIMS. Now, we've taken the exact same zircons we analysed on the shrimp. We've gone and done oxygen hafnium. And then we've taken those same zircons, what's left of them, dissolved them in acid, and gotten some really high resolution ages. There's only a few of these. It's quite an expensive process. But what we can start arm waving about, it does require more work, is we see that the Mount Stavely Volcanic Complex, this sample here is the Narrapummelup Road dacite member, is sitting down around 505, 507. We have our mineralised porphyries, 503 to 504, coincident with the Buckhorn diorite here, so similar ages. And then we have our friend, the Bushy Creek granodiorite, which is, in the CA-ID TIM space, distinguishably different and younger to what's going on here. So this really fits with the model that Dave has suggested, in that potentially you've got your flat-lying Mount Stavely Volcanic Complex being deformed and tilted upright. Then you have intrusion of the Buckhorn diorite associated with the mineralised porphyries. And then late stage, post-Delamerian or syn to post-Delamerian deformation, Bushy Creek Igneous Complex. So there's that's quite exciting. I think that's really interesting. We can also start going down the path in the research space as to when did the Delamerian actually end in Western Victoria? Is it a little bit earlier than what happened in South Australia, around the 490 in South Australia? Is it around about 505 or 500 in Western Victoria? Right, so on to the isotopes now. So we'll look at oxygen. Now, oxygen isotopes. In zircon, oxygen is quite robust. So it's reflecting, the oxygen isotopes in your zircon is reflecting the rock that melted, got squirted up into the crust, and then formed the rock that we sampled and got the zircon out of. Okay? So it's a good measure to indicate to us, well, what's actually happening at depth, what's melting, and what's going into that melt that's essentially growing the zircon. And what we find here is really interesting. Mantle zircon has delta O18 values within this grey band here. Most rocks that we see have oxygen isotope values up a lot higher, commonly up to around delta O18 values of around 20. So ours are sub-mantle oxygen values in our zircon, and that's really weird. But what it does tell us is, if you're in a subducting system and you were dragging down sediment into the trench and melting that sediment, you would drive up your oxygen values. So it'd be more recycling more sediment into that melt. We don't see that. So it gives us an idea as to what sort of systematics are going on in the Earth. And not only is it specifically one sample, It's all samples. It's the porphyries, it's the Mount Stavely Volcanic Complex, more or less, it's mantle-like, but it's also the granites as well. But how does this happen? So as I mentioned, if we're dragging down sediments, we'd be melting sediment, that would drive your oxygen values up, so you'd have higher numbers. But this is the really interesting thing. If it was only the porphyries that we saw sub-mantle-like oxygen values, we could play the game of saying, well, that's just some hydrothermal alteration of a parent rock that's melted and it represents those porphyries. But we see it in everything. So what the interpretation we've attached to this is, you've got a source that is at depth, and maybe a source for everything that we're looking at, the porphyries, the granites, and the Mount Stavely Volcanic Complex. Now, to actually drive down your oxygen values, what you need, well, one example would be you're melting hydrothermally altered oceanic crust. It's a possibility, particularly if you have some tearing going on in the downgoing slab, but there are other options that I'll come to a little bit later. So Hafnium. Hafnium works well with oxygen. We do it on the exact same zircon, so this is the exact same grains, 4 different techniques that we've used. And you'll also note that there's a complementary relationship to the oxygen in that in hafnium space, what hafnium tells us is how much continental contamination, continental crust contamination is occurring or melting. So rather than the oxygen telling you what sort of sediments are going in or water incorporated into the melt, this is telling you about the stuff above, so any of the continental crust or the supercrustal contamination that you might witness. And this suggests that if there was more supercrustal contamination, it'd be more evolved, let's say, you'd have values that get much more negative. But ours are quite positive, so it suggests that they're relatively juvenile in this sense. Interesting to note that the Mount Stavely Volcanic Complex is the more evolved out of all the samples, whereas most of the porphyries and the granites are the more juvenile in the hafnium space. So here are just sort of some summary slides and notes to what I've sort of rambled about in the last little moment. You read that at your leisure. This plot here is an interesting one. What we've done here is we've actually have the oxygen isotopes on the X, the hafnium on the Y, and we've coloured them. We've used the same colour scheme, coloured by age. So it's almost like a 3-point data set. And the way that we can sort of read this is, if we sort of trundle down this way, we're looking at more crustal contamination and more sedimentary input. Whereas if we go up this way, we're looking at less crustal contamination and less sedimentary input. So more juvenile, more evolved. And in this, we've been able to pull out a number of different groupings. The first of these are the porphyries and the Bushy Creek Igneous Complex. Have an age of around 502 to 500. And I will say these ages are now based on the shrimp ages, not Tim's. Okay. Relatively low oxygen, relatively juvenile in the hafnium space. Mount Stavely Volcanic Complex, a little bit older, has mantle-like oxygen and relatively evolved, relatively speaking, compared to everything else. We have an interesting a porphyry sample. This is the one that Dave alluded to, which may be reinterpreted as Mount Stavely Volcanic Complex. It's always good to have robust discussion amongst your colleagues. I'm not sure. I think it might still be a porphyry. It's a porphyritic rock. We can agree on that. And interestingly, if you recall in the previous slide, there was in an earlier slide where I mentioned that there was the Buckarandara on the edge in that sort of slightly demag zone. That plots here with the Mount Stavely Volcanic Complex. Slightly more evolved than the other Buckarandarite sample. So what we can use this for, what I'll do is just refresh your memory on where these rocks are. So we have the Bushy Creek Igneous Complex and the porphyries. The Mount Stavely Volcanic Complex, Narrapumlup Road, Dacite member, Tolway Toof. the interesting porphyry sits with the other porphyries. And there's that buckra and diorite sample on that edge effect that we see. So we can start arm waving a little bit now about where do we think things are melting and how they're going up into the crust and getting emplaced. So in the sense of the Mount Stavely Volcanic Complex, we interpret that based on its isotopes and age, we're getting some melting going on of the mantle wedge, some metasomatism, and that it's coming up and being erupted. Similar source potentially for the mysterious porphyry. Now what's interesting with the other porphyries in the Bushy Creek Igneous Complex, we interpret that potentially to get these isotopic values, you've got the downgoing slab, which has already been hydrothermally altered, and that could potentially be through black smokers at a much earlier stage. So you're somehow subducting a smoker that's hydrothermally altered that oceanic basalt, and which you've melted and then torn, and all the good stuff's come melting out and up. But alternatively, we could be seeing some remelting or melting of the underlying mafic plate. We also interpret that with the buckra and diorite, what may be happening is, as it's intruded into the Glen Thompson sandstone, which you may recall I said was highly evolved, what you're getting is you're getting a little bit of melting going on the edge of that buckra and diorite pluton. And hafnium, in the zircon sense, is actually really susceptible to change, particularly if you're interacting a juvenile hafnium signature with something more evolved. Add a little bit of sediment, which is the Glen Thompson sandstone. Oxygen's quite happy to behave, whereas hafnium, that's really going to drag things down. And that's what we see. That's what we see with this sample on the edge of the buckra. You really drag down your hafnium, but your oxygen, left to right, doesn't really change that much. So perhaps there's something going on just on that particular edge of that granite. So what do we actually get out of this study? We've provided some really good and really tight ages on some of the magmatic rocks within the Mount Stavely within the Mount Stavely area. And that we've also been able to look at some of the isotopic character and glean an idea as to what's actually melting to generate these, what's melted, what rocks have melted, and then been erupted or emplaced and grown zircon that we can actually get a character for the history of the tectonic evolution of the area. But who cares? It seems like a very academic exercise. But I guess, this is a fundamental set of data. It helps us constrain all the tectonic models that we see. It helps us work out, well, how do we actually form these porphyry copper systems? What's the underlying framework? So we always need to consider, well, what's the timing of events and what's melting to fully grasp what's going on in our system? Bit of shameless self-promotion. You can get these through the DOI, and if you wish, you may. I'm not sure if they're going to be made available, but come and speak to me if you wish for a copy. And I should acknowledge indirect co-authors, but Dave Champion and Dave Houston from Geoscience Australia, real leaders in the isotopic space, and sharing a lot of discussions and coffees with them. And I believe that's the end.